Hi folks, this is a little slide deck to describe how to do the Colab example of analyzing with deep learning the MNIST image dataset for handwriting. And it just goes through the steps that you need to do that. First, some little introduction, and this MNIST dataset's a very famous dataset, and it's designed to somehow benchmark and categorize approaches to recognizing handwriting, and there are various other methods, but they've all fallen into disuse compared to deep learning. And here we do not use here the best deep learning method, we use the simplest fully connected network to show how to use deep learning and also to run it on Colab. We're going to use the simplest fully connected network, or what we call the multi-layer perceptron, which is shown here. We've seen this picture before. We have the input layer. That's where the pixels, 784 pixels. So this here in the example is going to be of length 784 here, not 4. We have the weights, and we have an output layer. And we're going to use keras to construct this network, which will have actually a different number of hidden layers from shown down. So we're going to run on Colab. Colab is a pretty useful system. It has pretty well-known industry standards, if you like, or best practices. I think it's fair to say it's best practice in many ways. It uses a Jupyter notebook. It gives you a pretty reasonable CPU and GPU, so you can actually do deep learning. And the combination of the powerful software for deep learning and the Jupyter Notebook is actually a pretty good programming environment. And you need to have the web browser, not surprisingly. Presumably Colab likes Chrome browsers, although actually I run my Colab on Firefox. And you use Gmail account. One of my students has been suggested using multiple Gmail accounts, so you can cleanly separate your runs and actually get more total runs in that way. And here's where to sign on. And here's a very simple example Colab saying hello world in Python. And you say print hello world, and then you print the version of Python. And there's a rather good introduction by Colab, and all these files are saved in your Google Drive in this particular folder, I should say. With a little bit of hints about using Colab. You can there are these various shortcodes, plus code and plus text for getting code cells and text cells, but also there are buttons you can press to do the same thing. You can look at the keyboard shortcuts with Control MH, and you can look, if you want to look at what you can do at any time, do Control Space. And you just have to do it to learn how to program in Colab. All right, so we have we have 3 Colabs attached to this. These related introduction to deep learning material. The first is a general introduction to Colab, and it's at this cyber training site. We've already mentioned that one. Here is the one that actually is just a simple Colab. It goes through all your basic Python commands, just to show that you can run Python on Colab. Now you can show these slides are maybe a couple of years old, because when I wrote these slides, Keras was one of the preferred systems. Now Keras is still actually a good system, but it's got effectively totally merged with TensorFlow. At one time, Keras was a universal front end with some high-level commands, and you could use it to drive various different backends with all the detailed um, uh, deep learning technology built into them. So Keras allows us to define the neural net. We can't possibly do that on our own. It, um, we need to inherit the wonderful donation that Google with TensorFlow, Apache with MXNet, and Facebook with PyTorch have given us. The PyTorch system was built a lot on earlier work at Berkeley. And say Keras has a good expression, and PyTorch has a different expression, which is some people actually prefer. And Keras is mainly used to define a neural net, which will invoke MXNet or TensorFlow. But I say now it's really just TensorFlow. You can't use Keras with MXNet. And there are plenty of books on Keras. But just say these days, I think it's buy a book on TensorFlow. So you can just, when I write Keras here, think TensorFlow. All right. So we have here a nice Colab doing this thing, and the following slide has a video of me using that Colab. After that, we'll go through some slides with some detail. Okay. Okay, folks, here we are. This little video describes my experience using this particular Google Colab page available for the class, which looks at classifying the MNIST handwriting database. That's a bunch of pictures of the digits 0 through 9. Quite pretty, some of the pictures. And here we have the Colab. We, of course, go to File, Save a Copy and Drive. Then we get our copy over here, which is ready for me to change it. And as always, we go to runtime, let's do factory reset runtime. And then we can run, well, let's initially run all. So here we are doing the usual imports to get all our components. Here we have the Keras, possibly for the first time. Keras used to have a higher profile. Now it's got absorbed by TensorFlow. And normally you just talk about TensorFlow. But Keras is an important part of TensorFlow, making it somewhat easier to use. And the moment is probably running on this step, which is running through the epochs. I have set it for, actually the default is 3. I set it for 5 to, it's sort of interesting if you look at the accuracy. The first epoch is 0.87, not so great. Then it's second epoch onwards are almost at, they don't change a lot to 0.91 to 0.92. And you will not find a lot of difference between epoch 3 and epoch 5, for example. If we look here, we've up here, here we have a picture of the model.summary command, and here we have the plot model command. This thing here, just a picture of the 2 dense networks followed by an activation layer. And here's the input layer with 784 pixels. This thing is not using the fact it's an image, which we will later on do a convolutional neural network approach, which uses that as an image. This is just being thinking of this images as 784 pixels, which are just a stream of pixels, and we're trying to map those pixels into numbers. And we finished that now. We've got an accuracy of 975 here, and now that's on the training set, which has 15,000 batches each epoch. There are 4 images per batch, so 60,000 members. The test data set is 2,500 batches, 10,000 images. And you try to train it on one set of images, and then you test it on another, typically around 20% size of the total, because if you take a number to 0.8 times that number, you don't change the accuracy too much, whereas this gives you a clean set of images to test it. And here you can actually see the accuracy on the test data set is very similar to that on the training set, which is good. All right, so now we'll roar off and go back to the slides, this is part of the slide presentation. Thank you very much. You can see a bigger picture of me now while I work out how to stop the recording. So now we just go through the different cells in the Jupyter Notebook, which I actually did in action in the last video. And here we're just basically, the first cell here is basically setting up all the software. And you always have to look up exactly what you want. Here, they say this, if you did this today, you probably wouldn't use keras. Well, it still works because the code works, but using keras is not necessary. This is actually part of TensorFlow these days. Cloud Mesh is a technology we built, and it's used. It's not used actually in this particular Colab. It is used when we it's pretty useful for benchmarking. It allows you to time the different parts of the code. I made a very important discovery on which part of my code Python Notebook was taking the most time by using a stopwatch. All right, so now we have the different initial, what you might call the initial data engineering, and we have two data sets, which is quite typical. Sometimes you have three: training, validation, testing. Here we have training and testing, which is you don't have, I think it's sufficient to have two for many cases, and you just grab those by loading the data sets which already exist. And these are then downloaded. You then find the number of labels, which is probably going to be 10. And because everything should be classified as a number from 0 to 9. And then we use the so-called one-hot vector. We'll describe that a little later on. It means that we represent 0 as the binary digit 1 in the first position, in the 0th position, and followed by 9 zeros. So you have 10 digits in this label, and there is a 1 in the location corresponding to this classification. It turns out deep learning network, because of all these neurons and activation layers, likes that type of representation. And then we can read more on that, and these available routines convert us to use one-hot vectors. And now we say this data is an image, and when we do the convolutional neural net, it will exploit an image. And that's non-trivial, because remember, if I have a letter 2 in this case, I can actually use the 2D structure of that 2 which I can recognize with a convolutional filter to enhance my recognition ability. If I just do the fully connected network, all I'm doing is looking at this thing as an abstract set of pixels, and I'm mapping certain pixel combinations into the thing 0 to 9. So that's possible. I think it's obvious it's not the optimal. So here we are. We're doing the shape command in Python, and this is the image size. And then we do that for the testing and the training data, and we convert them to, we want them to be floating point numbers, and we also want them to run between 0 and 1. Whenever you do deep learning networks, you really have to be a little careful about the normalization of your input and also your predicted data, because neural nets have an absolute number attached to them because they have an activation layer, which often has number 1 is very important. Something special happens either at 0 or 1, because we're thinking of these as neurons, which are either on or off. So they're not continuous things. Actually, their great power is because they're not continuous, they can do a lot more than traditional continuous mathematics. All right, so we've now converted everything to be a floating point number between 0 and 1. And now we have to set up the neural net, and we can see what we have here. So we have here softmax is the things that converts everything to a probability. Sorry, let's start at the beginning. We define the so-called sequential model, which means we're just going to specify a set of layers one after another, and it assumes the input. The first layer is one of the input sizes, so that's the argument to this model.add. Then we're adding a dense layer with a number of hidden units, and we've set the number of hidden units, which is meant to somehow represent the internal information stored in the system, to 64. We'll come back to the batch size later on in the next slide. We've done so. And here we have the final output, the number of labels, and the softmax to tell us which is the most probable label. And then we produce a printout, which is a text printout with model.summary and a visual printout with plot underbar model. And those results are shown here. So this is the one I normally use. I happen to personally use this slightly more probably appealing representation. So we go from 744 input to 64. That's the initial hidden layer. The hidden layer goes from 64 to 10, and then where 10 goes gets activated on, and then we have the softmax. All right, so there we are. That is this layer, these three things listed here. Notice the number of parameters. We have almost 51,000 parameters we can change. These are the weights linking these layers together. Now we see what we actually invoke with the compile and the fit. The compile sets out the parameters of the optimization. We're using the so-called atom operator optimizer. We're using accuracy as a metric, and that's to judge the quality of the results. And we have a loss function, which is categorical cross entropy, which is a pretty straightforward loss function. And which is, remember, this is a classification problem. It uses slightly different loss functions from those that are familiar from continuous variables. And then we have preset the number of epochs to 3. We did that here. We set the batch size to 4. So this says here we have 15,000 batches, which means 60,000 images, which are the total data set. You go through a complete data set for every epoch. So this just iterates through the data set 3 times. And after every batch, it does an update of the weight parameters. So you accumulate you're trying to calculate a shift. So you're moving the weights from one place to the next. You do that with stochastic gradient descent. Stochastic means that you randomize everything you can, including the order in which these updates of these epochs are set up. They all have 60,000 images, but those images can be in any order. Then after every 4 images, you accumulated the derivative, and then you actually take that derivative, sum up everything using so-called back propagation, and then you add it to get new weights. If you notice what happens here, the first epoch doesn't get is incomplete. It gets to an accuracy of 0.87, and the loss, which is pretty high at 0.45. The later epochs, the accuracy hardly changes. It gets fixed to 0.91. If you change epochs to 5, as I did in the video I showed, it's still essentially at that value. The loss is still going down a little. But we now have to evaluate the model, which means we run it in inference mode, which we take the weights we determined from that training, and we just run the test set through that. And that gives you the test of 92%. If you run it, you will not always get 92%. I was getting 91.6 or 91.8. That's because everything is random. And depending on which images you actually choose, you're going to get slightly different answers. Here we have 2,500 batches in the test set, which is 10,000 images. And this is the end of this presentation, and it's extremely primitive. It only has a couple of layers. You can add actually more layers, internal activations, and you can get better accuracy. You can also use technology like dropout, which tends to improve the performance of the testing data set, because it tries to randomize things so you don't get locked into the details of the training set. But I say that probably the most important thing to do is to look at other architectures, such as recurrent or convolutional nets. With convolutional nets, the most natural, as this is an image problem. Okay, that's it for this very simple example. Have fun. Thank you.